So today we will learn last part of relativity, energy-mass relation. And this energy-mass relation is described by obviously the most famous equations out of all E equals mc squared.
Oh yeah.
E equals mc squared, which results in the producing enormous monster amount of energy. So let's add a little bit of energy, of monster energy.
Oh, that's why
So, where this formula coming from? It's not like Einstein sitting, looking into the ceiling and this, let's connect mass and energy in this way. No, this formula can be derived. There are a few ways to do it. There is a way how Einstein derived it, there is a way how later on people found that it's beyond school curriculum. In your textbook there is one of the examples of the reasoning, how coming to that, considering the law of the conservation of the momentum when the object emits photon, then absorbs photon. You can look through that. There is another way which I personally like more. If you recall that momentum equal mass times velocity, and if you recall the second Newton's law, how we write second Newton's law using momentum? Yes?
Wait, F equals wait.
Through momentum.
Here
Ft equals change in the momentum. Yeah? Can you recall this? Impulse equal change in the momentum, but that will work if force is constant. If force is not constant, then we can write it as F equal integral of dp over dt and differentiating using the product rule, we can find that dp over dt will be equal v dm over dt plus m dv over dt. I'm not going to show you all because it's going beyond what most of you have mathematical knowledge, probably except students who do special 3-4, you'll get able to understand the whole idea, but considering either moving objects moving slow, we will get through this reason, we can get that formula for kinetic energy that we have in the Newtonian mechanics, mv squared on 2 can be obtained from here, and energy, also recalling that we have energy equal, if you remember, Fs, force times displacement, and again, if this is not constant, we can get that energy will be equal integral of F ds over dt. Using those approaches, for small velocities we can obtain this, and for high velocity we can obtain mc squared. As I said, we don't need all that. I've just given you the idea that this formula not just was stated. Let's take E equals mc squared. It was derived and can be derived. You don't need to derive it, but you need to understand it and be able to use it. So, and now another thing. What is mass? This approach actually bringing us to proper understanding what mass is. Until now, what we are thinking about what is mass?
The weight of an object in
Amount or not weight. Weight is a force due to the gravity. No gravity, but still object will have mass. Mass, we was thinking about the amount of matter in the object, but it's not what it is. Mass is how much inertia object has. What is inertia? What is inertia? Now, come on. First Newton's law. What is inertia? Ability of the object keep its velocity unchanged. So if mass is a measure of amount of inertia, so the bigger the mass, the harder to change velocity of the object. And that's what mass is. And if you denote m0 as a rest mass, when so velocity equals 0, m0 is rest mass. Then mass at some speed, again it can be derived, will be equal gamma times m0. So as fast the object is moving, the bigger its mass, the harder to change its velocity. If you recall what the gamma is 1 on square root of 1 minus v on c squared. And you sketch a graph of the mass against velocity. Mass against v. And that will be m0, rest mass, how the graph will look like. How the graph will look like. When we approach in infinity, so when we approach in C, what we will have will be asymptote, vertical asymptote. So that will be exactly as the graph of the gamma, where this is C. So we have when speed of the object which has mass approaching speed of light, the mass approaching infinity. That's why any object that has mass cannot move, not just faster than light, it cannot move with the speed of light. Because it will have, at speed of light, it will have infinitely big mass. And to accelerate any object to the speed of light, we will need to apply infinitely big force. We will need to use infinitely big amount of energy, which is impossible. So from here we can see that none of the object that has mass can travel at the speed of light. Light does not have rest mass, so light can travel with the speed of light. Anything that has mass cannot. Object can travel close to speed of light. We still need to apply a lot of energy to accelerate even electron to the speed close to the speed of light, but not that much. Now, if we now combine these two formulas, we have that E equal, and so when object at rest, it has rest energy m0 c squared. This is a rest energy, when object not moving, rest energy. When object is moving, it has energy mc squared equal m0 gamma c squared. So how we can find kinetic energy? How we can find kinetic energy, energy related to the motion of the object. This is a rest energy. It's the energy that object has when it's at rest, zero velocity. This is energy of the object when it's moving with the speed v. How we can find kinetic energy?
m0 gamma c squared minus c squared.
Subtract one from another. Yes, well done. So we will have be mc squared minus m0 c squared. Substituting this, we will get kinetic energy equal gamma minus 1 times m0 c squared. This is a relativistic formula for kinetic energy, which we will get subtracting energy of the object moving at speed v minus its rest energy. The difference is kinetic energy. Now let's do calculations to compare the difference between the results that give us classical physics where we have kinetic energy equals mv squared on 2, which perfectly works when speed is not big. So let's take, for example, mass 10,000 kilograms, and it's moving with a speed equal half of the speed of the light. What will be its energy? What will be its energy according to the Newtonian mechanics? We have E kinetic equal 10,000 times 0.5 times 3 times 10 in the power of 8 squared. That's V divided by 2. And if we calculate, that will give us 1.13 times 10 in the power of 20 joules. Now, let's calculate the same thing, applying the relativistic formula for kinetic energy. We need to calculate gamma. Gamma will equal 1 over square root of 1 minus 0.5 squared, which will be given, can you calculate?
1.15.
Will be equal 1.15. So then we have relativistic kinetic energy. I will put dash to show relativistic equal gamma minus 1 will be 0.15 times 10,000 times 3 times 10 in the power of 8 squared, which gives us 1.39 times 10 in the power of 20 joules. So we have that actually kinetic energy will be significantly bigger than the kinetic energy.
No, it's minus 1.
Gamma minus 1. Yeah. 0.15 will be 1.39 times 10 in the power of 20. So object moving at half of the speed of light, its actual kinetic energy bigger than predicted by Newtonian mechanics, and bigger than mv squared on 2. At small speeds, the difference is negligible. When v is small, it will give you same pretty much result. But when speeds like this or even higher, the difference is very big, and we need to use relativistic formula for kinetic energy. Now, so as energy related to mass, that means mass can be turned into the energy. Let's do next calculation. If we will be able to completely turn mass into the energy, if we will take some useless student, let's take mass of 70 kilograms and calculate how much energy we will get if we will completely turn that student into the energy. So mc squared 70 times 3 times 10 in the power of 8 squared, that will be equal 6.3 times 16 times 10 in the power 6, 17 joules, 16, another 10, and 18. 63. That is, how big is this number?
Very big, pretty big.
This number is, will power Victoria, that how much electricity, electrical energy our state Victoria used in 70 years.
Yeah.
So, if you will be able to convert 70 kilogram into the energy, it will power the whole state of Victoria for 70 years.
I'm gonna
Now, in reality,
And that's what it's like.
In reality, there is only one case when mass completely can turn into the energy. Let's recall from Unit 1, when we're learning nuclear physics. What is this case? The only one case when mass completely can turn into the energy. Who can
Nuclear
recall?
fusion.
In
Nuclear
fusion, it's not
Fission.
not all of it.
fission.
No, not a fission.
Yeah. In the sun.
No, not in the sun. Not all mass converted into the energies. Only some part of it. We'll talk about that later. What? Nobody can recall.
It's over.
If we have particle collide with antiparticle, what is, if we have electron, what is the antiparticle to electron? Positron. Why positron we call anti-electron? Because antiparticle is exactly the same in all senses, it's same as electron, except one thing. Charge. Its charge is same magnitude but positive. So if we have one electron collide with the one positron, there will be annihilation happen. They both stop to exist and they completely turn into their energy. They completely will turn in which form? Electromagnetic wave. They completely will turn into the electromagnetic wave. But that's the only one case. By the way, let's calculate if they will be stationary. How much energy will be released? Mass of the electron and so positron is 1.6 times, sorry, mass, not charge, 9.1 times 10 negative 31 kilogram. So we have two of them, so energy released will be equal to 2 times 9.1 times 10 negative 31 times 3 times 10 in the power of 8 squared. So will be 1.82 times 10 in the negative 14 joules. 1.8. If I did calculation correctly, 16, 15, and then 1 with time, okay, negative 14, yes. Oops, thank you. I forgot to multiply by 9. I did just 2 times 9.1 and then times 9 again. So that will be 18 times 9, about 1.55. Let's round it to 1.6 times 1.6 times 10 in the negative 13, I think, joules. Can you please check my calculation?
Yeah.
Yeah? Okay, let's calculate the wavelengths. If, let's say, will be 2 photons emitted. As a result, because electromagnetic waves, we know that light can consider it as particles, photons. What will be the wavelength of this photon? We have E of the one of them will be equal 8 times 10 negative 14 joules, and we have E equal hc on wavelength. So we have 6.63 times 10 negative 34 times 3 times 10 in the power of 8 over wavelength, and that's equal 8 times 10 negative 14. So wavelength will be equal 6.63 times 10 negative 34 times 3 times 10 in the power of 8 divided by 8 times 10 negative 14. That will be approximately equal, approximately equal about 2.7 times 2.7 times 34.28 times 10 in the negative 12. Can you please check my calculation?
2.5.
2.5 times 10 in the negative 12 meters. Yes.
You get 8 times 10 to the negative 14.
This is the energy, because I said 2 photons are emitted, so I divided this by 2. When they collide, stop to exist, instead 2 photons are emitted. And
So you
this
divide that by 2, so that's...
I divided by that energy that was released by 2 because we have 2 identical photons,
And then that's energy of 1.
and use energy of 1 photon to find its wavelength. Can someone guess what type of the electromagnetic wave is that?
Gamma.
Yes, gamma. It will be gamma radiation. It will be gamma radiation. It's not something unrealistic, but it is a wavelength of the gamma radiation. Which can be, so these things can be detected. By the way, if you heard about such method of the medical imaging as PET, have you heard about PET scanning? Positron emission tomography. That's exactly how it works. If someone will be dealing with medicine, and PET scanning, which gives one of the very sensitive ways of produce medical imaging, PET scanning, it uses exactly this idea. The positrons are produced through the decay of the patient get injected with some radioactive liquid, and as a result of the radiation decay, the positrons emitted collide with the electron, annihilated, and that can be detected, measured, and correct diagnosis can be sent. So this has direct practical use for example, human health. Now, let's do the next calculation. 2 more calculations. Let's say helium, nucleus of helium. What nucleus of helium consists from? That's something that you need to know. By
2 protons.
2 protons, 2 neutrons. Helium consists from 2 protons, 2 neutrons. If you take mass of the proton, equal 1.6726 times 10 negative 27 kilogram. Mass of the neutron, mass of one neutron is 1.6759 times 10 negative 27 kilograms. So, and we have in the nucleus of helium, there are 2 protons, 2 neutrons. Can you please calculate what will be the mass of 2 protons and 2 neutrons? And mass of the helium nucleus is 477 times 10 negative 27 kilograms. If you add 2 protons, 2 neutrons, what you get if you add 2 and 2? 6.69 7 times 10 negative 27 kilograms. And this is a mass if you take 2 protons, 2 neutrons. And this is the mass of the helium. Let's subtract minus 6.646. We get tiny difference, 0.051 times 10 negative 27 kilograms, or 5.1 times 10 negative 29 kilograms. It's a tiny difference, but there is a difference. There is a difference. And let's calculate how much. So if you take 2 protons, 2 neutrons, and put them together, fuse them into one helium nucleus. It happens not through the one step, it happens through, if you can recall when we did in year 10 astrophysics, there was 3-step process, but delta M, that's what we have found. So how much energy is released is 5.1 times 10 negative 29 kilograms times 3 times 10 in the power of 8 kilograms. This energy called mass defect, this one that we have found, it is a difference between mass of 2 protons, 2 neutrons and helium nucleus. Because mass of the helium is less. What does it mean? That when they put together, some mass turn into the energy. Then what we need to do, if we want to separate helium again back to 2 protons, 2 neutrons. If energy was released, what we need to do then with the energy?
Put back in.
We need to put back in. Put some of the energy in. And we get that. So that's called binding energy. That's what's called nucleus together. That's why it doesn't fall apart. Some energy was released. Now we need to put it back. Now in the sun we have hydrogen fusing into helium. Hydrogen fusing into helium. And let's calculate the next thing. Sun emit every second, so power of the sun equal 4 times 10 in the power of 26 watts. How we can measure it? We can actually measure it. How we can measure it? Any ideas? How we can measure how much energy, because power is energy per second, how we can measure how much energy sun releases every second? Not particles, it's electromagnetic waves. We can measure how much energy falls on 1 square meter on Earth. And we will have that will be pretty much brightness of the sun or intensity of the sunlight, which equal total power divided by 4 pi r squared, because sun emit energy evenly in all directions. So if we do this, and we know distance from Earth to sun, that we can measure. We can put device and measure how much energy falls in 1 second on 1 square meter. And using known distance to the sun, we can calculate the power of the sun. Let's find, because where this all coming from? From mass turning into energy. Let's calculate how much mass sun loses every second. We have this, because this is per second. So we have in 1 second, it's lose 4 times 10 in the power 26. It's joules, how much energy it emits, equal mass times 3 times 10 in the power of 8 kilogram, delta M, how much mass sun loses. So delta M will be equal to 4 times 10 in the power 26 divided by 9 times 10 in the power of 16 will be equal about 4.5 times 10 in the power of 9 kilograms. If I did it correctly, calculations, 4.4.
So does that mean there's eventually going to be no sun?
So, every second, sun losing that much mass.
That's a lot of math.
That, because sun produces a lot of energy, because a lot of mass, through every tiny process of fusion, which each process releases tiny amount of energy, but there are a lot of them, that much mass lost by sun every second. Sun becomes lighter every second. It was good question about for when sun will lose its all mass. The thing is, it before, what will happen, can you recall again what we learned in year 10?
It'll expand to a supercharge.
It will run out all of hydrogen. Hydrogen will fuse into helium, and then what will happen? It will turn into the red giant. The core will collapse, and then, not completely will collapse, and then helium will start fusion into the carbon. But outer layers will expand, and Earth, unfortunately, will go then inside of the sun and stop to exist. So we need to find some solution to that, what to do. We still have a bit of time. It's in about 4.5 billion years before sun run out of hydrogen, but still need to start thinking about that, what to do. And then sun, when the old helium will fuse into the carbon, what it will turn?
White dwarf.
Into the white dwarf. Yes. So we'll build just a very hot ball of carbon. Nuclear fusion starts. It effectively will stop to be a star. It will be like slowly cooling down to become a black dwarf. Yes.
But that's the power measured from the Earth. So wouldn't it be a little bit less than what it actually is? Well, because
No, we measure at the Earth. We measure how much energy
isn't
flows.
some of the higher wavelength light reflected by the atmosphere?
Take that into account.
Yes, you are right. And I guess probably the proper measurement, because we can do measurements outside the atmosphere. So I think that number was obtained when it was measured from the outside the atmosphere. Yes, absolutely right. Atmosphere will change our measurement on the ground level. Okay, that's pretty much how the energy related to mass. Like, subscribe and donate to help fight terrorist countries and organizations, support Ukraine and Israel.